All right, so we've got an electron going clockwise and we've got the radius, right? This is our radius of curvature in the plane of this page, right? It's doing that because there's a magnetic field, right? And we know the magnetic field is either into the page or out of the page. So really we've got a 50-50 chance there. So the best thing I think is to draw a picture of this thing going clockwise. So that's not a bad circle. Right, so there it is, it's going clockwise, right? So that means at this moment, this negative charge, right? This negative charge is going this way. And we know that this is its velocity, right? It's tangential to that circle. So your velocity will be tangential. The force making it go around this circle must be this way, okay? So that is our magnetic force making it go in a circle. It has to be toward the center, right? Remember, if this thing's going in a circle, centripetal force has to be toward the centripetal force is toward the center, right? By definition. And then the acceleration would be just parallel to that, right? So it'd be, right? So the acceleration, if they ask you to draw acceleration, it's going to be toward the center. The force is toward the center. The velocity is tangential, right? And this thing is definitely going clockwise, like it says, right? Okay. So now the question is, which way is that magnetic field? Okay. So what you want to do is you want to put your index finger this way, right? Index finger that way. Your thumb is going to point this way, right? And if I do that, make sure you use your right hand, okay? My middle finger is pointing out of the page. But remember, this is an electron, so it's going to be opposite that, right? So the magnetic field that's making this happen is into the page. Now, really, you've got a 50-50 chance, right? So what I do is I always do that prediction the way I just said, right? And then I just, I do it again, right? It's like, okay, to the right, into the page, the force would be up the page, but it's an electron, so it's negative up, it's down the page. And indeed, that's the direction that we want it to go, right? Okay, and then has a velocity. Okay, so draw the velocity, we did that. The magnetic force, we did that, right? Acceleration vectors, we did that. Calculate the magnetic field. So the key here is that the magnetic force is QVB, right? And then also the centripetal force is mv squared over r. And these are in the data packet. Okay, I think this is in like check section 6.1 or something like that. Okay, and you're going to just set these guys equal. So QVB equals mv squared over r, right? And so it says calculate the magnetic field, state its direction. Okay, so we're solving for B. So we're going to cross off a V. Don't forget to cross off a V. And then B will be mv over qr, right? And just plug your numbers in. This is the mass of the electron. Look it up in your data packet. This is the velocity that you have right there, okay? Q is the elementary charge, right? So 1.602 times 10 to the minus 19th. And the radius is this, okay? So just plug those in and you're set. You can find the magnetic field, okay? And then notice that's milliteslas, right? So 7.91 times 10 to the minus third Teslas is what the answer should be, okay? And then it says, show that the magnetic field is given by B equals mv over ER. Well, we kind of did that, right? mv over, and then the charge would be E, right? So Q is equal to E, and then substitute that in, and you're there, right? So we did that, right? Okay. Okay, show that the period of its motion is given by this. Well, see, that's interesting, right? So let's think about this, okay? We need some other things, right? So we're going to use QVB equals mv squared over r. I think I'll erase here. I'm going to erase in 3, 2, 1, erasing. Okay, so here it is. It's going in a circle, right? Okay. Here are the things we're going to use, okay? We're going to use the fact that the magnetic force is QVB, right? We're going to use the fact that the centripetal force is mv squared over r as it goes around the circle, right? Okay. But here's the other cool thing, right, is that velocity, any velocity in a circle, is just distance divided by time. The distance in a circle is 2 pi r, and the time to go around is defined to be the period, and that's the same t that's there, right? So now you can see there's like a 2 pi there. It's like, that's tempting, right? Okay. So what we're going to do is we're going to say, okay, t is, I always like to start with like the thing. T is going to be 2 pi r, the distance divided by the velocity, right? Okay. So then take this thing and solve this for the velocity, right? Okay, so QVB equals mv squared over r. Solve this, don't forget to cancel a v, right? Solve that for v. V equals some expression, and plug that in to here. Now remember, it's in the denominator, right? Okay. Once you do that, you'll still have a q in there. Remember that q is equal to the elementary charge, okay? And you ought to be able to get that. Now, the thing that's kind of interesting about this, okay, is that notice that the velocity doesn't occur. It isn't in this thing. The velocity actually just cancels out. It just depends on the mass, the charge, the magnetic field, right? So presumably, if it's going slowly, it's got a small little radius. If it's going faster, it's got a bigger radius, right? And they use this fact. There's something called a cyclotron. This is the cyclotron period, right? Typically, we talk about the cyclotron frequency, which is just frequency is 1 over period. So the frequency would be EV over 2 pi m. Okay. Now, as long as the mass doesn't change, right? And for a relativistic particle, the mass will dilate, right? So the frequency will have to change. Okay. But if you keep it, below say 20% the speed of light, right? You can speed things up in a cyclotron and use the same magnetic field. As long as it's the same particle, has the same charge to mass ratio, it works. It's really cool. All right. I don't know, do they use cyclotrons for electrons? Maybe they do, I don't know. Usually protons for sure, right? Okay, so show that the period, we did that, right? And then it says, what is the relationship between the velocity and the radius of curvature? Well, let's solve for the radius, right? QVB equals mv squared over r, right? So v cancels, and we get r is the momentum, notice, divided by q times b, right? So this is what tends to make it go straight. This is what tends to make it curve, right? That kind of makes sense. Okay. So let's see. If we increase the velocity, then r increases. If we increase the mass, r increases, right? If we increase the charge somehow, right, r would decrease. And if we could increase the if we could increase the magnetic field, r would decrease, right? So increasing anything in the denominator makes this decrease. Increasing anything in the numerator makes it increase. Yeah? All right, I think we answered the heck out of that question.